Everyone, we're doing 21.2 permutations and probability, and I just want to take a second to talk about a number of ways to order things. So here I have a marker, a rock, and a die. And there's this way to order them, but I could also order them like this, where it goes marker and then die and then rock. Similarly, I could put the rock first. If I do that, I get marker or rock, marker, die, or I could go rock, die, marker. So that's 4. Similar, the very final one is the die first. So I go die, rock, marker, and then the very last one is die, marker, rock. So there are a grand total of 6 ways to order those. And this kind of makes sense. I'm going to make a little table here. So if I have 3 items, there are 6 ways to order them. And this makes sense because when we put the marker first, we decided that there was 2 ways to order these guys, right? There's this way and then this way. So if I have 2 items, how many ways are there to order those? Well, as it turns out, it's 2. There's 3 items, it turns out it's 6. So we just multiply that by 3. This multiplying thing brings us back to our factorials. So as it turns out, 6 is equal to 3 factorial. 2 is equal to 2 factorial. So if I ask you how many ways there are to order 4 things, well, there's 6 ways to order these 3, right? And then I just have to rotate through the 4 items to be first. So that means this is 4 factorial, which is equal to 24, and then 5 factorial, which is equal to, what is it, 120? It's kind of helpful to memorize these first few factorials because you'll be using them a lot. So that brings us to permutations. And permutations are simply selecting items where the order matters. And the first example here with the letters is the exact same I just did, where we have 3 items, and then we have to choose 3 of them, and the order actually matters, what order we choose them in. So again, I could choose marker, die, rock, or rock, marker, die, or however I want to do it, right? There's 6 different ways to choose those things. It's going to get a little more complicated if I told you, oh, choose 2 of these things, right? How many ways are there to choose just 2 of them? Well, we can work through it because there's only 3. It's not too hard. There's marker, die, and then there's marker, rock, and then there's die, marker, and then die, rock, and then there's rock, die, and rock, marker. So those are our 6 ways. But it's not super intuitive how to calculate that or how to get into it. So we need a framework to go through this. The general framework that we're going to use anytime we're doing these sorts of things, these permutations, is going to be called the fundamental counting principle. And this fundamental counting principle simply says that if there are n items, so in this case there are 3, and there are A1 ways to choose the first item, so in this case, since there's 3 items, there's 1 way to choose the first item, right? It could be any of these 3. So we choose the 1. Then there's 2 ways to choose the second, right? Or 2 ways to choose the second, and then 1 way. So this is equal to 3 times 2 times 1. So 3 times 2 times 1, which equals 6. Again, that's 3 factorial. This will be a little bit different if we're doing something like flipping a coin. Let's say I flip a coin. This is called being able to choose with replacement, because if I get tails or heads the first time, does it affect how my next one is it's heads or tails? Let's say I have to flip a coin 4 times in a row, and I need to figure out the number of different ways I could flip a coin 4 times in a row. I could get like tail, heads. I could get tail, 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 or I could get tail, tail, heads, heads, or there's a bunch of different ways I could do it. But let's count how many ways. How many ways are there to flip the first coin? Well, it's 2. There are 2 ways to flip the first coin. How many ways are there to flip the second coin? I could get heads or tails still, right? It doesn't matter if I've gotten heads before. There's still just 2 ways to flip the second coin. How many ways are there to get the third? It's 2. How many ways to get the fourth? It's 2. So the number of possible number of possible patterns for 4 coin flips is going to be 2 times 2 times 2 times 2, or 8. right? So we can rely on this fundamental counting principle as a framework to discuss some of these problems, even though it may be kind of new or different. So we'll jump into some examples. There are 7 members in a club. Each year, the club elects a president, a vice president, and a treasurer, right? So there are 7 members. We're going to choose president, vice president, treasurer. And even though we talk about choosing one first, the order here really isn't important. We're just going to pretend like, you know, we have to choose a president first, and then the vice president, and then the treasurer. But note here that the order doesn't really matter, but it helps us conceptually think of the probabilities by doing one at a time. So that's why we're doing it. What is the number of permutations of all 7 members of the club? We've done this, right? Boop-a-doop-a-doo, it's 7 factorial, which comes out to 5,040. So that's the number of ways we can order those 7 people. And imagine we would just take this number of 7 people, just shuffle them up, shuffle, 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 right? That's the total number of possible ways we could order them together. Is 5,040. Then it says the club is electing or holding elections for president, vice president, and a treasurer. How many different ways can these positions be filled? So we have our 10 people here. These are people. Pretend they're people. 6, 7. Okay. How many different ways can these positions be filled? Well, how many ways are there to choose the president? Or how many different people could become president? Well, there's 1, 2, 3, 4, 5, 6, 7. We could choose any of the 7 to be president, right? We're assuming that, you know, all chances are equal and stuff. But there are 7 possible people that could become president. How many can become vice president? Well, again, there's 1, 2, 3, 4, 5, 6. Now that the president has been chosen, there's only 6 ways. So we can think of 6 different ways. You see where I'm going with this. How many ways are there to choose a treasurer? Well, 1, 2, 3, 4, 5. Any of these 5 could do. I'll put it on this guy. So the grand total, right, how many different ways those positions could be filled is 210, because it's 7 times 6 times 5. And we can see that this 7 times 6 times 5 is just a portion of this one here. I'm going to skip ahead here. This 7 times 6 times 5 is 7 times 6 times 5 times 4 times 3 times 2 times 1, but we've eliminated this part here, right? We've divided 7 factorial by 4 factorial. 4 times 3 times 2 times 1. Why would we divide it by 4 factorial? Well, as it turns out, we divide it by 4 factorial because it's inconsequential what order these remaining 4 people are in. We really don't care, you know, what order they're sitting in or what order they're in. So it doesn't matter to us. So that's why we divide by 4 factorial. And as a general term, we can come up with how many people we can divide by. It's the number of people here minus the number of the officers. So in this case, we can come up with a general term where we take the number of objects, right, that we're choosing from, and then divide that, or make it factorial, divide that by the number of objects we're choosing from minus the number we take at a time. So in this case, in this instance, how many we actually are choosing. So it's 7 factorial over 7 minus 3 factorial. The book is a general formula right here. We describe this as n choose r permutations, where there's a little n here, a little r here. And the formula is n factorial over n minus r factorial. So again, if I were to use this example, I would do 7 p r, which in this case is 3. So I'd read this as 7 choose 3 permutations, something like that. Okay, we'll do another example. It says a certain motorcycle license plate consists of 5 digits that are randomly selected. No digit is repeated. What is the probability of getting a license plate consisting of all 7 digits, all even digits? Well, first off, we need to think about how many possible license plates there are, right? 5 digits. The digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 different digits, and we're just choosing 5 of them. So we can do 10 choose 5 permutations. We can plug this into our formula, right? So it's 10 factorial out of 5 factorial, because that's 10 minus 5. 10 minus 5 factorial is, use a calculator. You get some giant number, 30,240. Okay, these are the number of elements in the total sample space that we want. Event A consists of permutations of a license plate with even digits. Therefore, we need to figure out the number of elements in set A, right? Or how many possible license plates there are that just have even digits. How many even digits are there? Well, we're going to count 0. So that's 0, 2, 4, 6, 8. That's it. There's only 5. So we have to choose 5 out of those 5, right? There's no other, basically we're just reordering these 5, so that's 5 factorial, which is 120. So our final probability is simply the number of elements in event A out of the number of elements in our sample space. So we just divide them. 120 out of 30,240, right? There are 30,240 possible license plates. Only 120 of them contain all even digits. Therefore, the odds of getting one of these license plates is simply 1 out of 252. So less than 1%. Okay, go ahead and pause here. See if you can figure out these ones real quick. So pause. What is the probability that the United States will win all 3 medals in an event when there are 8 finalists? So again, it's 8, choose 3 permutations. We put our 8 factorial up here, 8 minus 3 factorial down there. That gives us our total sample space. And then the number, there are only 3 Americans, right? So what are the number of ways we could have those 3 Americans? Well, there's only 6 different ways for gold, first, second, third. So that's 6 out of 336, or 1 out of 56. What is the probability the United States will win no medals for this event? Same deal, except this time we're going to choose, there's 5 different people that'll work for this part here. So the sample space is the same. It's still 336, right? There's 336 ways to that race could have gone, but only 60 of those ways are there no Americans at all in those in the top 3. Okay, I'm gonna pause it there. Yeah, I'm gonna make another video with some more stuff that's pretty important. So watch that.